like 3 times to put on Instagram. I never received that. So this fascination. So now what reading my parents go is the one that has to create the they're use these those birds one. Normally, yes, so like mine is a big one. I has moved to this is all the like this is all the one. It's even smaller. Like how like technology sorcery. Not sure we have a PhD science outline for explaining this. So how else do we use? You get one more back. You drive that by rapid thinking. I think absolutely. It is the future plans. We have to do it. Really? Actually, welcome to the talk. So today we have one of the and this is during those work at zero science and at Harvard. As we used to talk about how to find aids. Welcome. It's great to see you here this evening. Thanks so much for the invitation and accommodating my schedule to be on. I really appreciate that. So yeah, what I'm really excited about is the question of finding life in the universe. And like just said, I went both the science department and the astronomy department. So I think there's a real parallel between research for ancient life on Earth and questions about the origin, emergence, and present pose of life on Earth. The switch over beyond the solar system, across the solar system and beyond it on exoplanets. And what's really exciting about this moment in time of solar system exploration and with exploration of exoplanets is we're really on the cusp of being able to really sort of scientifically ask this question about whether or not there's life on the planets, the objects that we're looking at. Which is enormously exciting, but I want to emphasize in this talk, I think answering that question poses major challenges to our understanding of planets as non-biological entities. And in fact, there's a huge kind of hurdle of understanding non-biological processes on planets, which we very before we can know in any given setting we have to determine things as well. So that's sort of what I'm going to kind of work towards over the course of this talk. Um, well, I want to begin by sort of putting a simple statistical framework around this question of finding aliens. So let's imagine we've got a population of planets, and we do now have such a population of planets, both within our own solar system and beyond, where many thousands of planets have been discovered around other stars. And amongst all of these planets, some fraction have aliens, and we create a pretty picture now just kind of where the Venn diagram. So some subset of these planets have aliens. And obviously those are the ones we need to find. That's where the Nobel Prize obviously lies in looking at those planets and not the boring ones surrounding the ones. How do we find those planets amongst the many thousands of planets we discovered? Many of which, most of which perhaps will be lifeless. We don't know how big this circle is as a proportion of the total planet population. That's one of the things we have to go and actually discover. At the moment we know that there's one planet amongst those 6,000 or so that host life, and maybe it is one, or maybe it's a higher fraction. We've got to go and look to find that out. But how are we going to do that? In the solar system, in principle, right, you could land on a planet of your own. You could look around and you could see life sitting there drinking its latte, and you've got a um, unfortunately, it's not going to be a happy value in the solar system. It's not going to be that easy to set up. Exploration of Mars is a search for ancient life in its sediments. Exploration of Venus is presenting questions about what's happening in the clouds of Venus. It's not yet this kind of search in a simple place is not presented to simple challenges landing on Earth, hitting a tree and solving problems. So it's even harder than when we distant planets. We've got far less fast data that we can gather on, so our ability to characterize them is much diminished. So what we're really looking for are biosignatures, and this is often used, with particular meaning in the context of exoplanets. The signature that we're looking for in life is often very particular, and I'll get onto that later. But we can think of this much more, generically. If we're looking in the rock record on Earth, a biosignature is a fossil, right? There's evidence of past life. And so when we're thinking about when did life originate on Earth, the very natural question to ask is, what's the oldest rock we can find, and what can we look for in that rock, which is a fingerprint of life having been around when the rock formed? That's basically a biosignature search on Earth, the planet we know that has life, but at some point presumably didn't, and we're looking for that frontier. And that's obviously putting that frontier in ongoing geological question. So I just want to kind of think very generically at the moment. We've got some planets. We're looking for a fingerprint of life that we can see on those planets. And what I've done here is shown that emphasize that the thing we're looking for, the signature, doesn't have to be a unique fingerprint of life. So I've drawn a circle for the so-called biosignature that overlaps with the aliens, but not completely, and actually overlaps extensively with planets that don't have aliens on them. So that would be a false positive, right? So if we now look at this planet population, we see some with a biosignature that don't have aliens. So that would be a false positive. If we kind of shout out aliens we found, we'd be wrong. These are all these planets around here are true negatives. We've not seen the biosignature and they don't have aliens on them, so that's great. We know not to spend any more telescopes. These planets over here, we've looked at them and we've not seen the biosignature. Yet, they're covered in coffee from the aliens. Well, we missed that. We looked for the wrong thing. So it's only in that middle region, which are kind of yellow and gold here, where the true positives. These are the planets where the biosignature, something that we see which is saying, there's actual life producing that signature. So I'm trying to be very abstract at this stage, and I'll come on to the specifics later on. So this is, this is the exercise, this is the statistical framework I have in mind. Really, obviously, very, very simple, but I think it's useful. Like, this is a challenge we face, especially, and it gets harder and harder the less data we've got. So like, find a coffee cup, you feel like pretty confident it's the product of there's going to be few false positives for like coffee cups and stuff on works. But when we're dealing with gases in an atmosphere, well, there are lots of ways to produce small molecules in atmospheres. Light is one of them. Maybe not the only one. You know that there's actually there's non-biological ways to make quite complex molecules as well in astrophysical environments. So the problem becomes much harder when that's what we're dealing with, not the gratuitous elements of life that hits a coffee cup with a fossil. Now, sort of historically, or during the 20th century, this question of searching for life has been conducted in a different way. And for many years, it was, the search for life was not the search for life has been conducted now with James Webb and looking at planets outside the solar system. It was conducted as a techno-signature search. It was a search for technological life, broadcasting in the electromagnetic spectrum, radio waves, its presence to the galaxy. And it was a question of listening out for the TV, the TV channels of technological life in the nearby galaxy. And we're like, yeah, again, great. We've seen the television, we've seen Channel 3 from that planet. Again, we solved the problem, we found life. And in this statistical, kind of very simple statistical framework, what we've done is we've moved the biosignature circle onto the alien cell. Because what we're looking for is we're looking for electromagnetic radiation that's in an organized kind of series of noughts and ones coming up from our planet. Again, it's very unlikely to have a kind of non-biological false positive. That's not something the universe, a planet, is just creating in and of itself. It's not, you can't go back into a rock record and find a TV program like it. That is directly live. So the false positive rate has become really small. It's great. It's a really precise biosignature. Um, and that's what I'm showing you. This is the unreaded Gorman telescope, which is being used for these techno-signature searches today. It's looking at different star systems and looking for organized electromagnetic radiation being broadcast from them to find technological life. So this is a search that's ongoing. And the logic of it statistically is that you've got a very low likelihood of having a false positive if you get kind of organized electromagnetic radiation coming back. The problem, but what maybe makes it challenging to be confident that you'll get a positive result, is the history of life on Earth and what that says about the likelihood of technological civilization emerging. So this geological time scale represents about 2.5 billion years. 2.5 billion years of Earth history. Earth history goes back further than this, a further 2 billion years beyond this diagram. Normal life really only kind of blossomed into existence about 500 million years ago, and humans and technological civilizations only in the last kind of moment of time in our history. Hominids arriving a million or so years ago. So it's only incredibly briefly that we've been a technological civilization broadcasting our presence electromagnetically into the galaxy. So a few hundred years out of 4.5 billion years. And if we look on the galactic scale about what that means, this is a representation of the Milky Way. This is the center of the Milky Way. This is where the sun sits in its suburban location, out on the edges here, very pleasant. And this is the little bubble onto which Earth's electrons broadcast of which 200 light years in diameter are in the galaxy. So you can see that an absolutely tiny fraction of the galaxy in which we put down a footprint of our technological existence with electromagnetic broadcasts. That presents the technological civilization may arrive right late in the life of a planet. We don't know how long they'll last. And even when they do get going, it takes a long time for that human properties to if it's moving weaker to expand out into the galaxy. So the problem with this, or the challenge this approach faces, is that whilst it's maybe got a very low false positive rate, it may be that the true positive rate is extraordinarily small. We don't know the occurrence rate of life on another planet. The occurrence rate of technological life is surely a function of the rate of life itself. So it's a fraction of a fraction, which itself may be a small number to begin with. So this is a problem, or a problem, searching technological life. So what I'm going to focus on is sort of what's occupying directly or indirectly the field of planetary science and exoplanetary science, which is the search for life with biosignatures that aren't, which are kind of passive in some sense. They're imprinted on the planet by life's operation without needing to be technological. So an example in the context of Earth would be the oxygen in its atmosphere, which is a direct product of biological activity and represents in some senses a biosignature. There's those kind of fingerprints that we want to think about, which, for exoplanets use gases in atmospheres primarily. We can sort of put an equation behind the Venn diagram, which is the probability of aliens given that we see a biosignature is the true positive rate over the true positive plus false positive rate. So simply the area of this unit to the area of a whole blue circle. And how I draw it here, this is not a precise biosignature. Most of the time we see this biosignature, actually, you found it on a planet that has no aliens. That's the problem we have. So given the signal we've seen, you can have a biotic hypothesis. You could be proposing, well, we've seen this gas in the atmosphere, that must be due to life. Or you could be able to big and you could say, oh, that's probably not life, it's a volcano or something like that. That would be the abiotic hypothesis. And I suppose personally, my approach would be that the biotic hypothesis is almost like a hypothesis of last resort. That would be how I would view it. Right? To claim that we found life requires ruling out, knowing that the abiotic hypothesis is for some reason not a feasible explanation of what we see. So the question is, well, how do we rule out the abiotic hypothesis, or how do we avoid false positives? And what I'm suggesting is that that requires context. We need to know an awful lot about the planets. We can be confident that the thing we're seeing is not just what the planet's up to of its own accord. That it actually needs the intervention of life to produce that signal. So we really need to know a great deal about the planet we're looking at. And that itself is a massive challenge, given the data that we have. A very exciting one. Um, it's what my research is interested in, but it's a necessary stepping stone to making the claim that we discovered what we love to be able to do and be super excited. So I want to give an example to it. Now, I'll start with this gas, the H3, phosphine gas, it's a poignant gas, and it's being discussed as a biosignature gas. It produced, one of the places it's produced on Earth is by decaying organic matter. So this image at the bottom is the wetlands of Tierra del Fuego, and decaying organic matter in these wetlands releases phosphine. So here is a gas produced, in this case, directly by on a. There's also phosphine in the atmosphere of Jupiter. Phosphine was discovered some decades ago in Jupiter's atmosphere. So here's a biosignature gas, a gas that's been talked about as a biosignature, which is seen being produced on Earth by the action of life in the atmosphere of Jupiter, a planet which largely people are not talking about as being inhabited by aliens. So what's going on? What's interesting, I think, right, the phosphine presents a kind of interesting story here because when it was discovered, it was an anomaly. That when phosphine was found in the atmosphere of Jupiter, it was a surprise. Like, oh, Baker says there's phosphine there, we're at Jupiter. The models of the atmosphere of Jupiter said that phosphine should actually be really deep in its atmosphere. So this axis here is saying this is 5,000. This is the depth from the top of the atmosphere of Jupiter, getting deeper and deeper into it. This is 5,000 times the surface pressure of Earth. 5,000 times? That's not right. 100,000 times the surface pressure of Earth down here. And at this depth, yeah, there should be phosphine in the atmosphere. But right up the top here, where we've actually made our observation, there shouldn't be any phosphine at all. So the observation of phosphine was a surprise. It was an anomaly. But what it led to was not the conclusion that there must be life on Jupiter producing that phosphine, but that our physics, our physical understanding of Jupiter is wrong. The model, which is predicting what the atmosphere should be like, is missing something. The physics it was missing was turbulence in the atmosphere. It was not factoring upwellings from the deep atmosphere where phosphine is produced into the low pressure, high region of the atmosphere where when phosphine gets put there, it's actually got a reasonably long or a long enough lifetime that it can handle when it gets discovered. So what's been taught us about an abiotic process on Jupiter that we previously not fully understood. The atmosphere is vertically mixing more vigorously than previously believed. So in the context of our diagram, we think what's the context telling us for having seen phosphine on Jupiter? Well, it is a biosignature, sure, but the context actually tells us that the planet we're looking at is kind of obligate uninhabitable, right? A vast atmosphere of mostly hydrogen gas, with no surfaces. There's only very, very minuscule region where maybe you actually get good water, if at all. It seems highly likely to be uninhabitable, and we can roughly understand phosphine as a result of vertical mixing in Jupiter's atmosphere. With the process which actually underlies the beautiful kind of changes you see on the surface of the planet generally. phosphine, as you may know, or you may remember, phosphine has been claimed to have been detected in the atmosphere of Venus as well. And this is some of the data in one of the discovery papers. I don't want to really focus on the data, but because there we don't know obviously about is it and to really even showing the phosphine. I don't want to touch on that, but just to say that here again, another planet in the solar system, we've currently found a phosphine group. On Earth, to do with life, Jupiter to do with mixing the atmosphere. On Venus, if the phosphine is there, it's actually really hard to understand why the phosphine is in the atmosphere. It's been a real struggle. People have employed a lot of creativity to try and understand why or how this molecule can be present in the atmosphere of Venus. And it's extremely challenging to understand why it should be there at all. So it's tempting to go, well, given it's so hard to get my model to predict this molecule to be present, maybe the observation is wrong. And that's like clearly an important question to ask. The other thing is, well, maybe it's life, or maybe it's just some other bit of physics or chemistry you haven't understood. And this is in the solar system, rather. So this is with planets that in the case of Venus, we landed on Venus. So these are happening incredibly well. And we're having these debates around what the data mean, whether the data are real or correct, and then whether that data can be interpreted as light, or is just some other physical chemical process that we've not yet understood. Either way, if the data are, then either way we have something really exciting to learn. But it's very hard to know definitively whether it's light. So what's the kind of what's the component that we kind of move through in the question about how we found evidence? So the first stage, and this sort of charts really the history of exoplanetary science. The first stage is discovery. In 1995, the discovery was wow, there is a planet around another star. An extraordinary discovery of a Jupiter-sized planet orbiting extremely close to its host star. A planet that kind of shouldn't have been there. From the perspective of our solar system and our solar system architecture, the first discovery in exoplanetary science, was a fundamentally alien object compared to what the solar system had taught us happens when planets fall around stars. So brilliant. And then, that pace of discovery picked up in the early 2000s, 2010 with the Kepler mission, thousands of planets discovered. Now, many smaller planets, Earth-sized, going down close to Earth-sized planets. The discovery of a planetary star, the first step then to getting to a question where you're wondering whether you've seen an alien or not. The second stage is actually deeper observation of those discovered planets. You need to characterize them. What's their size? How massive are they? What we know about the star? What's its UV spectrum? What's the composition of the star? And what's the composition of the planet's atmosphere as well? Can we see what gases are in the atmosphere? Or even whether there's an atmosphere at all? All of those are the kind of next stage kind of observations. After that, we want to use those observations to start building the picture of the planet. At this bottom, at the discovery stage, kind of the discovery and characterization stage, we basically got you take those beautiful pictures of Earth from space, you see clouds, continents, oceans, they're beautiful, and just replace it with like a grey circle of the same radius. That's like where we are in the first stages of this program. It's a planet, which is fantastic, but we essentially know nothing else. We need to go from these basic properties into, to fill in that picture, to infer once in the atmosphere is what the climate might be like on the planet, whether there's liquid water at the surface, whether there are clouds. This is then the next step. And from that, from knowing the context, then we can start interpreting some of the observations we've made, say the composition of the atmosphere, in terms of abiotic and biotic processes. And clearly, we need to kind of go backwards and forwards between these. As we build the context of the planet to match with the observations, we're necessarily constraining the type of abiotic processes that could take place. For example, a planet that's really hot tends to have a molten surface, it's an entirely magma-colored planet. And that fundamentally changes the kind of physical exchange between the interior of the planet and the atmosphere that can take place, compared with a planet like Earth, where you need to have a volcano to the interior atmosphere interaction. So I think this is like the kind of process, and largely the field is sort of around this zone, I think. The James Webb Space Telescope, certainly for small planets, the frontier lies kind of right around the characterization stage. Like, for these planets that are maybe a couple of times the radius of Earth, can we find an atmosphere on them, and can we characterize the composition or chemistry of that? That's kind of where the field is at. For larger planets, because the observations are sort of easier to meet or has a higher precision, we're able to move further up this hierarchy. But the larger planets are the planets we're thinking necessarily that they're going to have aliens on them. So we know any kind of one, we're in, you know, an obligate abiotic regime. So let's just kind of look at the data a second. So I want to share a couple of examples just to kind of the actual data to show why it's sort of challenging to interpret. Um, so largely this data is being obtained by the transit method, and that's what this cool video shows. We're looking at a distant star, and the planet orbiting that star happens to pass between the star and our line of sight. So the planet's obviously smaller than the star, so it doesn't cause an eclipse, but it does dim the star, and a little bit of the star's light blocked out by the planet, and that creates this dip in the brightness, which is what's being plotted here. It's for it to be defined the star gets a little bit dimmer, a bit fainter. So that's been an extraordinarily successful method to discover planets in the first place. To go beyond that and actually characterize them, the same method can be used, but now what gets done is that we look at the size of this transit, the depth of the transit, as a function of wavelength. So we look at light of different colors, for different wavelength, and, and see how deep the transit is in those different colors of light. And the reason that can tell us about the atmosphere is because atmospheres absorb electromagnetic radiation, and we know that from the fact that Earth is not really cold on its surface is because it's got CO2 in its atmosphere, and CO2 is absorbing infrared light from radiation. And that's the same in exoplanet atmospheres, carbon dioxide in them. They can have a range of other molecules, which certain molecules absorb light, and by doing that, they change the effective size of the planet. So you can imagine a bare hot planet is that black symbol, and that gives you one transit depth. And if you then put an atmosphere on it, and the atmosphere is carbon dioxide, which absorbs at a certain wavelength, then the light at that wavelength gets blocked and the planet looks a bit bigger. So that's what's kind of being illustrated here. And if you then plot the size of the planet according to the wavelength of the light, you get data, you get kind of the next kind of triple wasp 107 is that the planet 30 times more massive than Earth. It's has a radius of one Jupiter radius, so that's 10 times the radius of Earth, and it's on a 6-day orbit. So this is not a planet which we're going to think is a good one to throw aliens on. But the data are beautiful and absolutely extraordinary that we've gone in a couple of decades from discovering planets, having previously had no knowledge of these planets existing anywhere else in there outside the solar system, to now measuring water molecules, the amount of water, sulfur dioxide, potential presence of planets in the atmosphere of these giant planets. So these are extraordinary data, and the orange line is the model. This is the model that's been fixed, and you can see there's really strong features in the data. It's really very clearly not a flat line. You clearly need stuff in the atmosphere of this planet to explain the data we're collecting. But this is a massive planet, and being a large planet, it means that the higher signal when it passes in front of the star. Now we move to a lower mass planet. This is beta masses, 1/5 of Jupiter radius, so a couple of times radius, on a 33-day orbit. It's K218b, it's a very famous planet, and it sits really at the frontier of our ability to prove potentially habitable exoplanets. This is also James Webb data. You can see now, though, compared to the size of the features in the spectrum, and the blue line is a model, there's a lot more scatter in the data, basically, and you can see the error bars and those points. You can see there's kind of a little bit more scatter. So the data are an extraordinary accomplishment. But you can see that going down to a planet that's now, a few times less massive and 5 times smaller, we're beginning to push back against the observational limits on what we can do. And so this is a planet that's a so-called sub-Neptune. It's less massive than Neptune. It's bigger than Earth. So it's kind of intermediate. And it's a really awkward place for us to have landed observationally because we don't have planets that fall in this gap between Earth and Neptune in the solar system. So the only way we can know anything about this type of planet is by looking at them around other stars. And this is the data we've got to learn everything about these planets. So that represents a really extraordinary achievement in understanding their physics and chemistry, which is, like I said, I think is essential before we go on to interpret data like this in terms of the presence or absence of life on these planets. And I just want to kind of come back and draw an analogy to, the exploration of ancient life on Earth and in the solar system. Two examples. This is the solar system example. This is that meteorite near H84001, a very famous meteorite that landed in Antarctica um, and was brought back and studied in detail. So this is a microscope image. I think I probably blocked out the scale. Well, you can see a scale down that's 250 nanometers. This is not what we're seeing in here, but we're seeing a feature of a nanometer scale, this thing here in this meteorite, which is a little cluster or a little string of magnetite particles in this room. So that's actually mostly under an electron microscope, and then little absolute crystals connected together in the seam. And it was noticed that this pattern of crystals looks very similar to a pattern of crystals you'd see in certain magnetic material on Earth. And this led to the speculation that what we found in this Martian meteorite uh, was evidence of past life on Mars. And then we can give a built in some life on Mars, saying that we find potentially discovered life on Mars. There may be design communication. Obviously, that means that we're interested. The people who started been tested, I think, probably large number of people believe it is not evidence for life. But here is the magnetic bacteria, and it doesn't hide it. It's truly they look very similar. And they're not wildly different appearance. But this just shows how hard it is when you're dealing with ancient rocks and you've got only kind of the echo of life present. You haven't got the bug crawling around in the rock anymore. You've just got its echo, its kind of footprint left. How difficult it is to distinguish the living or once living from the never. And here, there are plenty of non-biological ways to get some crystals to grow and change. But biology also does it. So it's kind of like a double on that. A similar problem exists in the earth sciences looking back in time. So two different examples. So one of the most recent forms of life on Earth is stromatolite. It's a kind of algal mound, and they still exist today. They're kind of algal mounds that do photosynthesis. They just below the water, there's kind of a layer of algae on the sediment, and they kind of build up. So they kind of create like clumps like this in the sediment. And so, you're looking for ancient signs, some of the most convincing fossil evidence for life, ancient life on Earth is kind of mound like this in the sedimentary record. These are layers of sediment, and they've got these bumps in them. But again, it's like a textural observation, and there are other ways to make lumps in rock. Another way is shown here. This is another ancient rock, but this is interpreted to be a non-biological kind of mound in an ancient sediment. So when this is the kind of signals you're dealing with, the problem is extraordinarily difficult. From to K2ATP, the A molecule that's being fit into this spectra, so you can these bumps in the you need molecules in the atmosphere. And one molecule that's being fitted is dimethyl sulfide. From features, as you can see, kind of in these long wavelength regions of the spectrum. And that's a really exciting molecule to have potentially found in the planet's atmosphere. And the reason is, yes, dimethyl sulfide on Earth is a product of and actually dimethyl sulfide, which is produced in the oceans, is a major cloud condensation nuclei. So it's produced in Earth's ocean, it comes up on the oceans into the atmosphere, and clouds condense on these dimethyl sulfide molecules. But they don't accumulate in the atmosphere, and what we don't need to focus on what's happening here, but it's also showing pathway to break dimethyl sulfide down as well. It ends up getting oxidized in the atmosphere and producing sulfuric acid, and the sulfuric acid drops. So, dimethyl sulfide is an interesting example. So we've got the data set we saw on beta and TB, and there's this region of the spectrum, a certain wavelength, where if dimethyl sulfide is present, it will absorb light. The challenge is, the absorption of light at a particular wavelength is not necessarily an enormously unique feature of any one molecule. And here's a whole bunch of molecules people have pointed out, and the absorption features are roughly the same wavelength as the sulfide. So there's a major, it's kind of the analysis to kind of think, yeah, science and biology design for the research texture in the rock. Mike could make that, and then start thinking on one. And how do I rule out Norway to convince myself I'm next with life is the only I have? So I really need to know the context. All these other molecules that absorb in the same region, they'll have certain stabilities they might not exist at. Certain temperatures, certain pressures, in the presence of other molecules you know are present. So you need that context to start ruling all of these other possibilities out so that you can leave yourself with dimethyl sulfide and then go, yeah, I've got dimethyl sulfide, and maybe life is indeed universal producers. So what we want to do is move our kind of context circle from over here over to so that we're finding biosignatures when the context convincingly overlaps with aliens. I just want to quickly move through this fantastic diagram because I think that's an interesting points to make. So organized like this, we do have false positives, and it's hard to imagine with the kind of data we're going to be getting that we'll be finding there'll be no false positives. There's probably always going to be a false positive rate. There'll be lifeless habitable planets as well. So that's what draw my opinions. It was there are planets that could in principle host life, but are not showing any biosignatures, and so presumably lifeless. And I find that actually really creepy. Like you imagine, I almost like this kind of like sci-fi, slight kind of horror vibes movie, where you landed on this beautiful ocean, planet, beach, so everything going on. Nice. Right, yeah, no one's home. Where is everyone? Right, that's these planets in this diagram. It's Earth, maybe 4.4 billion years ago, just after its formation. It cooled down, the water condensed out of the atmosphere to the ocean, yet no longer refugees. We have no idea how prevalent such habitable but uninhabited planets are. And I think that'd be quite so you can failure to discover life will be fascinating because it will tell us something about how hard it is for life to originate. We know on Earth life originated very early. Fossil record goes back for 3.7 billion years and gets more contentious after that. But there seems to be reason to think life emerged really very quickly on Earth. We don't know whether that's good, that's what's necessary to learn about technological life, or whether that's just how it's always going to happen. But discovering planets that are habitable and lifeless will tell us something, which is really fascinating. This is life as we know it. It's aliens on a habitable planet, but they just aren't producing a biosignature that we can see. And actually, Earth is another good example of that. If we think about the obvious biosignature of oxygen in Earth's atmosphere, Earth's atmosphere only became oxygenated about 2.5 billion years ago, and only reached modern levels of oxygen maybe 500 million years ago. So about half of Earth is in the oxygen-free atmosphere. So if that's what we were looking for, oxygen's our biosignature, we would have just gone straight past Earth as no hope. So whether or not the bisignature circle overlaps the alien one. Obviously, it depends a little bit what you're looking for, what collection of things you're looking for. But just to highlight, we know that life, even on Earth, has changed its fingerprint in the atmosphere significantly over geological time. This is the ideal case. This is life as we know it. It's on a habitable planet, and it's great. It's producing a biosignature. We can find it. So that's kind of discoverable life. This is another kind of exciting region of the diagram. This is aliens on planets that we don't think should be habitable. So that's the region where, silicon-based life or life in sulfuric acid and stuff like that comes in, or Carl Sagan's, life in floating around in the atmosphere of the sun. All that kind of exotics comes in down there. And, I really hope all of that life exists. That would be super cool. It's very hard to know how to look for it. So I don't think it's unreasonable to kind of look for the life, broadly speaking, we understand, which is sort of what's implicit in the structure of this diagram. So this is all false negative territory, life that we've missed because it just happens not to be produced in the demand structure, life we're not even looking for because we're not bothering to look at these planets too closely, they're super hot or something, we think they shouldn't have life on them. Uh, this gives us the abiotic race, the race which life emerges on planets, which I think astronomy, I think exoplanetary science, in a way, the only way we're going to get this. So even if we discover a deep version of life on Earth, which would be, an amazing breakthrough of organic chemistry, maybe, Earth sciences together, if that discovery is made of how life, originated on Earth, we're still not going to be able to really answer the rate at which we should expect that to occur on other planets. That really requires empirically going out and looking and seeing whether there are all of this sort of things. False negatives. This is making the point about cancer evolution on Earth. In a bit more detail, it's the green curve of the oxygen. This is billions of years ago. We're over here at the present. Obviously, in a conveniently high oxygen atmosphere. For half of Earth's history, there was essentially no oxygen in the atmosphere. And then for the other half of the oxygen was millibar levels the length at that time. So if you've got to be careful, this is just another way of saying that you've got to have a way more general understanding of how life imprints itself on an atmosphere than, say, just, our modern oxygen-rich planets. Um, so what if we think about things in our planets to really put this, what context is important? Um, I think one of the key pieces of context is context that constrains fluxes. Like constraining the flux of molecules through a planet is really critical context. For understanding, seeing a given biosignature gas, something that could be produced by life, whether it really requires life for us to explain its presence in the atmosphere. And I want to use that. So let's say we've seen phosphine in the atmosphere, like we might have done in Venus. Well, given the environment of Venus, given the temperature of the atmosphere, the number of UV photons that are hitting that atmosphere, we can calculate how quickly that phosphine is being destroyed. So that's this arrow here. This is the destruction flux of this biosignature. Okay, so we've seen it there. It's probably not, we probably didn't happen to just catch it before it disappeared. So if we're seeing it there, that means that, and it's being destroyed at some rate, that must mean that it's being supplied at an equal rate to keep it there in the atmosphere. So this is where our abiotic model comes in. It's like, well, what processes can you think of that produce phosphine in this atmosphere? Produces it at enough rate to explain the abundance that we're seeing. And the answer here, as I'm drawing, is no. This is the most we can do with our non-biological model. So that could be volcanism, it could be meteorites coming to the atmosphere, whatever, and get creative. If that was all that was in, then we should see an abundance that's this small. But we actually see this much. Okay, regrettably, I found an alien. Too bad. That's the Novartic hypothesis. We actually then need a model, chemical, physical model, biological model, of what could be making this molecule. Can one itself make enough of this molecule to explain its presence? What I haven't shown, but the third possibility is, well, we can't think of something just instantly or biology. We can put a biological model that produces a flux. But I mean, it seems pretty hard to believe that life will be producing it in this crazy rate as well. So the possibility is, which part of Snowden's observation in life is just a weird, anomalous observation. So, yeah, which is just happens obviously on like a non-like model. But that's not a good place to be. Again, there's missing physics or chemistry that we're going to learn here on one way or the other. So, how do we learn about fluxes, the way planets move molecules around inside them into their atmospheres? Well, we need to know about their bulk composition, what they're made of. Is it a rocky planet? Because then the way in which it moves molecules around is going to be decided by the way rocks move things around and how quickly they move and what elements they can transport. So that's going to be true for small planets. Small planets down here, looks at maybe 10 planets. If it's a really massive planet, then it's probably a giant ball of gas. How do we call it Jupiter? Giant balls of gas can have vast upwellings from their deep interior up into their higher atmospheres. And they can move the material around in a completely different way. And we've got to then also know about the structure and climate. So you could have a planet that's mostly made of rock, but it's 3,000 degrees. Well, that planet is sure it's made of rock, but that rock is all now molten and have the viscosity of water. So that planet's also going to move material around in a completely different way to another, when the rock is indeed moving around in its interior extremely slowly, which is also the heartbeat through the picture. So all of that's like a critical context we've got to build to start thinking about how fluxes of molecules move through planets and end up in our atmospheres to explain the abundance of molecules that we're seeing. And I think the really exciting thing is, the really exciting question is, what are the interfaces in planets? So here's a kind of a view of the Earth, and we're seeing I guess one major interface between atmosphere and land, and maybe another interface between atmosphere and space. Both of those interfaces are critical for setting the composition of the planet's atmosphere. Molecules are lost to space from the top, and molecules enter in the bottom from volcanism, from interaction with the seawater with the atmosphere, and obviously the biosphere. Interfaces on planets are enormously dynamic. For instance, this is a video from lava entering the sea in Hawaii. And you can see all the kind of processes going on interfaces in one place. We've got gases coming out of the magma, chlorine, sulfur, carbon, oxygen, hydrogen bearing gases. And those same gases are dissolving back into the sea, where they'll eventually be precipitated out as minerals. But in the meantime, they produce their gas in one form, and they'll end up as these species in the atmosphere of the Earth, hydrogen chloride, sulfur dioxide, CO2, carbon dioxide, H2, before they find their way back out of the atmosphere into rocks and minerals through the action of seawater. And in the meantime, these are gases that we can potentially see in Earth's atmosphere. And indeed, after any major eruption, you will see sulfur dioxide lasting for potentially several years after a major volcanic eruption. So the types of interfaces in planets, their interior structure, is really important. And what exoplanetary science has shown us is that there's probably a huge diversity in planetary interiors to explore, which for someone who's trained in earth scientists, it's super exciting because it means the diversity of geology, speaking loosely, is really wide, with some analogs in the solar system and some totally new exotic kind of worlds to explore. So I just want to kind of skim through these super briefly. At one extreme, you've got planets that I'm calling high density, but planets with no atmosphere. So they're bare rocks. So the analog in the solar system would actually be Mercury, and we'll have ones which are very cold or relatively cold. So bare atmospheres just being sputtered by radiation and atoms thrown out of their star. These bare rocks will get hotter and hotter, and then they'll melt. And you've potentially got atmospheres which are just vaporized silicate rock above a magma ocean. This is kind of Mercury analog. We've got in the big band, we've got sort of Earth-like planets, so Earth itself at the Q end, where we've got water mediating the chemistry of the atmosphere significantly. Venus in the middle, when the planet gets a bit hotter, a massive CO2 atmosphere, but potentially volcanism ongoing, and potentially the atmosphere directly reacting with the rock at the surface. It's so hot. And then again, the hottest end, the planet will just start to melt over a few thousand, over 1,000 degrees. It'll start to melt, and eventually the whole planet will be molten. This time with a reasonably thick atmosphere above the magma ocean. And then finally, so I'm just going to skip over that. Sorry. And finally, we've got the planets that have a bigger atmosphere, or it's getting so massive that it's sort of maybe you think of it as an envelope. It's a thick layer of water or hydrogen, other molecules mixed together. And again, we have an interesting solar system analog of these types of bodies, which are the icy satellites of the giant planets, Europa and Enceladus. These are sort of analogs for these water or, yeah, kind of water dominated objects where beneath that thick layer of water might lie some rock. An interesting question is here, right? Well, how does this rock, a deeply buried rock beneath hundreds or thousands of kilometers of ocean, interact with the ocean and then ultimately the atmosphere? And these planets, too, as they get closer to their star, will heat up and potentially melt, meaning you've got this continuum from a molten interior all the way through to this hot steam atmosphere. So this is like an exotic realm we've not got a good analog for in the solar system, that may actually be prevalent among the exoplanet population. So I'm just going to end by, yeah, context in the search for life when the context is aliens. So, like I said earlier on, this is these are the solar system planets, and then there's this gap, right? Jupiter, Uranus, Neptune, Earth, it's Mercury. We've got a gap in the middle in terms of size. And these are the sub-Neptunes. So this is in terms of the observational frontier today that we can most readily probe with James Webb. It's the atmospheres of these intermediate mass planets that we have no analog for. They're super abundant. This is a histogram showing their abundance as a function of size. So they're this population. So some of the most abundant planets in the galaxy that we've got an analog for, we've got to discover by looking at. And excitingly, there's been a great deal of disagreement on what these planets are made of. So there's a hypothesis the sub-Neptunes are literally mini Neptunes. They're just a small Neptune. This is suggesting that they're molten balls of rock, that they've got vast liquid water oceans, or that they're kind of some giant hydrothermal, kind of steamy, hot rock interacting with high pressure water world. So there's all this diversity of interpretation that's led to a great deal of uncertainty over what these objects are. So that's kind of, from the perspective of looking at them and being confident that one's seen aliens, that's kind of a problem because we can't even agree on what they're made from. I think it's super exciting nonetheless because this is the question. The structure and climate and habitability of these objects is the first question. Like going to structure I introduced earlier, this is this is where we're at. We've observed them, we're beginning to characterize them, and we want to take the next step to infer their properties. And to do that, requires a lot of creativity and imagination and good physical chemical models. Lays the foundation for then going back and reinterpreting what we've seen in the context of abiotic and potentially abiotic processes. And that's the frontier of the field today. And I think it's a really exciting interface between disciplines that I'm supposed to look at. So thanks very much for very much for the wonderful talk. For questions, we have this chat box, which you can ask questions by talking into the box, and we can talk it around. Any questions?
So my question would be like, I understand all these telescopes, they was back in time for millions of years ago, and we understand that the light was originated from thousands of years ago. So why are we looking back in time to search for the money?
Yes, and there is something really interesting. Yeah, something really interesting that exoplanetary science allows us to do is to look back in time. But I think the way in which it primarily allows us to look back in time is by the fact that the stars we're looking at are at different ages. So I think broadly speaking, the planets that we can make any kind of good observations of, they're within a few tens of light years, which means the light that we're seeing from them is only a few tens of years on. So we're looking back in time, but not massively far. I might actually be born yet from the planets we've been looking at, but the planet hasn't changed very much. But what is true is that because the stars are different ages, they're potentially billions of years different in their age that we're looking at. So their kind of geological clock is very different. So we're basically looking at them today, plus or minus, minus 10 years, maybe 20 years, whatever. But they're potentially a system that's only had 2 billion years of life, or 1 billion years of life, or maybe a few hundred million years of life. And exploring time in that way is actually really exciting and important. And so some recent discoveries have been made simply looking at the occurrence of planets and the architecture of planetary systems on young stars, and discovering how planets change over time because they interact rotationally with each other and maybe throw each other onto the system, or they get irradiated by their stars and start losing their atmospheres. So that kind of thing is already starting to be looked at in a really exciting way. It tells us about the early life of planets in planetary systems and how the system of ordinary years may have got to the state it's in by virtue of processes that happened in the last few hundred million years as well. So we can time travel, and that's super exciting.
Biosignature instead of like
Uh, so I think like the nature of this, I guess I suppose my view is that we're always looking for a high signature, no matter what we're doing. We're looking for a signature of life, rather than the life itself directly, because that's just not the nature of the observations we've got. We're looking for its fingerprint in the atmosphere of the planet, say, or in the geological sense, in the textural fabric of the rock. They're both signatures of life, they're not the life itself. Yeah. It's, um,
No, there's a person on the back. Oh, your question. Yes.
what would you see in terms of light years? Because the cutoff is going to really think that the data we're observing now, like, is no longer relevant to what the planet is at this moment.
uh, yes, what's the size of the, I don't know now, shape students for ignorance. But I think, like, geologically speaking, the Earth has been, the chemistry of Earth's atmosphere, so ignoring humanity's pollution of the atmosphere in exciting and detectable ways. Earth's atmosphere has been Earth's atmosphere for 500 million years. Like, in 500 million years, light leaves our galaxy. Well, very easy. So, um, geologically speaking, if we could look at planets anywhere in the galaxy, we're basically seeing planets today, is my view. With the caveat, with the exception that these planets may be around stars that are only billions of, in which case we're only seeing a planet in the first billion years of life. And that would be super exciting to me to get that kind of slides. But we're not really, I don't think we're really looking back into the past of a given planet. If you see what I mean, we're looking really into the past of planets in a statistical sense by looking at a planet that is around a star that's only a billion years old.
So as long as it's within our galaxy, it's pretty like current data.
Yeah, with the exception that we can actually only make good observations of planets that are in like the nearest few tens of light years. So that's been also the transition in the field in the last kind of decade or so. Is the first mission that discovered thousands of planets very far from Earth, which was great in the sense it gave wonderful statistics of planet occurrence rate. But the problem was that because they're far away, they're faint. And because they're faint, it's very hard to get the kind of precise data that allow you to estimate whether there's CO2 in the atmosphere. So,
for another illuminated detection.
Yeah, so what is meant is that we then focus our search of planets in the nearest 100 to 200 light years, so that we find planets that are around bright stars that we can then go and look at and actually characterize the atmosphere. So that's the distinction between discovery, where you can find and discover planets around stars, but if you want to characterize them, you're asking for like 1 or 2 orders of magnitude more from the data in terms of precision, and then you need to kind of come to much closer planets. And so actually we are kind of limited in a sense. Like there's a volume, the very nearby volume galaxy is what we can current technology actually explore in the context of by signature searches.
Thank you.
Thank you. I'd like to ask, what is the frequency of finding compounds which we cannot explain abiotically, but are also not known as signatures of the life out of knowledge? I'm just kind of like pointing at the question, what if the type of metabolism that produces all these molecules is actually an extremely rare type of lifetime? And so just kind of trying to find the things that are like physically and chemically difficult to explain might suggest it's like life as we do not know it.
Yeah. So I think my philosophy on this, which is I mean Carol Newland has made it point, is that we should be looking for anomalies. So I think that probably is the right way to conduct the search for life, is we should be looking at planets, in this context, it's basically in their atmospheres with exoplanets. And we should be asking, like, what can we not understand about the gases we see in this planet's atmosphere, given, the physical chemical processes that, the planet, the abartic planet will just do on its own, volcanism or whatever else. And then you've got a bucket that everything's anomalous. Some of that anomaly, maybe all of it's going to be not my ignorance about volcanism, right? So some of it might be my ignorance about biology. And so if I say, okay, I've got there's the non-biological processes I can model. These things I can't explain. Then I can go, okay, well, what are the biological processes I can model? Right? With, I guess, Earth-like metabolisms. That might explain some of what's in this bucket of anomaly policies. And then maybe after both things, there's still something left. Then it's just, it's not, I can't say it's not, it's an anomaly. It could be a biological origin, it could be a non-biological origin, it's just an anomaly. I think you went pretty fast. So we can have way of saying, I think we should be open-minded about what we're looking for. And but equally, stretch our abiotic model as far as possible. So, another example of Venus is Venus has ozone in its atmosphere. Earth has ozone in its atmosphere because of O2 in its atmosphere. Venus does not have O2 in its atmosphere. The presence of ozone in Venus' atmosphere is another in Venus's atmosphere that you can't explain the abiotic model. You can't explain the biological model, because any biological model is going to be on life, which would be very dead on Venus. So, Venus is to me, is like a fantastic example of we're finding anomalies, and we're not going to explain them either way. So, what's going on? Yeah, I don't know. We'll go for one more question. Let's focus.
Hi. You mentioned the James Webb telescope and the extra data that it's given us. Is there another generation of detectors that's about to appear? And if so, what are your hopes?
Not enough. True. So I guess the answer is no. What was really there's another thing to be very something. So there's the Plato mission is going to it's a more question like from the outset, right? Has been what is the occurrence of truly Earth-like worlds? Earth-like planets around sunlight stars. We don't really know the answer to that. And that's a simple observational challenge. Finding an Earth-like planet around the sunlight stars is hard. It's far away from the star. You can't move on to the star once a year, which is kind of a long time to have to wait and stare at a star. So we've been really not successful at finding that, and this method will give that to this. So in the next decade, we should know the occurrence rate of Earth-like planets around sunlight stars. Would be a fantastic data point in the kind of rate of life in the universe, or kind of are we going to find loads of habitable life as well? So that's the one thing I think is going to be super exciting, just on the pure kind of demographic side, what's out there in the universe. The other thing is, by the end of this decade, also there'll be ELT, so ground-based telescope, that's a mirror, which will be able to do high resolution spectroscopy of very nearby planets. So it'll be able to do it for a small planet, but very nearby small planets. So approximately, and maybe roughly outside kind of the star surface, should be able to be has atmosphere created the L's. Again, super exciting, right? So maybe the nearest planet to us is just teeming with life, and maybe we'll have an answer to that in the next decade. But really, to go beyond that is going to be extraordinarily challenging with current technology, and really requires a next generation of space-based telescopes, which currently are only in the kind of planning stage. They're not funded. There's no commitment to launch them. They can't from new technology that's unproven. So, and that, yeah, that's kind of on one level a bit frightening, because that's going to be decades before we maybe have an observatory that's going to look at 10 and hundreds of potentially habitable and inhabited planets rather than just the nearest few. But that's the kind of timescales now field is going to cover on, which means that in the meantime we're going to be getting the most out of facilities like James Webb, which is small planets are going to get looked at, but it's always going to be challenging to pull out a rich amount of understanding of their atmospheres, certainly if they're small and cold with current technology. Yeah.
Right. I think that's the last question that we'll take. Thank you very much for the wonderful talk. Thank you everyone for coming and hope you have a good rest of the night.